Good day. For those of you who do not know us, we're the instructional staff for ECE 150, Professors Hiren Patel and Werner Dietl, and Douglas Harder. In this topic, we're going to discuss the call stack. Alright, in this topic, we are going to review and then describe the call stack. Specifically, we're going to see how the call stack can be used to allocate memory for both parameters and local variables. We will look at two examples in detail. Alright, up until now we have seen that local variables for main have their memory allocated at the bottom of memory. This is the region called the call stack. Now, from main, we have functions that may be called, and those functions will have parameters and local variables. Now, let's recall the behavior of a function. A function is always called from within another function. It has arguments that are passed, and then when the function that was called returns, it generally returns some sort of value, unless of course the function was declared void. Notice that you can never jump into the middle of a function and start executing it. You must always start at the beginning. Now, once a function returns, you cannot go back to that function and continue executing that function. Also, you cannot access any of the parameters or any of the local variables. That information is now gone once the function has returned. The other thing is functions may call other functions. So from within main, you may call a function which may then call the absolute value function on some value that's being passed to it. The absolute value function will then return, and the function you called will then make use of that returned value. Alright, so suppose that local variables of main are stored at the bottom of memory. Here we have 8 bytes that are allocated for the local variables of main. So perhaps main has 2 local variables of type int, or perhaps 1 local variable of type double. When we call a function from within main, we must allocate any memory that's required for the parameters of the function we're calling, but also for the local variables within that function. The obvious location is to use the space that is immediately above the memory allocated for main. Alright, let's see how this works. Here we have a program that prints out the GCD of 2 numbers. So within main, we initialize 2 local variables to take on the values 42 and 91, and then we call the GCD function, which will then calculate the GCD of the 2 arguments. Note that the GCD is being calculated of val1 plus 10 and val2. Let's tabulate the information. Main does not have parameters, but it does have 2 local variables of type unsigned int. The GCD function, if you go back and take a look, has 2 parameters, each of type unsigned int, and there are 2 local variables, temp and remainder. Alright, so if we execute this function main, there's memory allocated for 2 local variables, val1 and val2, and they are initialized with the values 41 and 91 respectively. When the GCD function is called, memory is allocated for 2 parameters. So memory for m appears just above the memory allocated for val2, and memory for the parameter n is assigned above that. Now, the values that those parameters will be initialized with are the values of the argument. So one argument is val1 plus 10, which is 52, and the second will just be val2, which is 91. So now the values of the arguments are copied up into those locations. All right, the GCD function also has two local variables, temp and remain. So now we can assign the memory for those two local variables. They would just be assigned in the space above the memory allocated for the parameters of the GCD function. Now, the first conditional statement tests whether or not m is less than n. And if we see that, that is true. And so therefore we will execute the consequent body of that conditional statement. The first thing we do here is we initialize the local variable temp, and it's initialized with the value of m. So the value of m, 52, is copied up. All right. The next statement assigns m the value of n. So what we will do is we will copy over the value 91 and place that into the memory flagged for m. Okay. The third statement, n is assigned the value of the local variable temp. And so n currently has the value 91 and is now assigned the value 52. All right, so we've completed executing this conditional statement. Looking at the next conditional statement, we see that it is false and therefore not a problem. The consequent body will not be executed. Instead, we jump to the next statement, which is a declaration of the local variable rem, and it will be initialized with the calculation m modulo n. Now, m modulo n is going to be 39, as that's the remainder that's left over. So rem is initialized with the value 39. All right. Next, we'll go to the while statement. The while statement has a condition. We check, is rem not equal to 0? Yes, it is non-zero, and therefore we will execute the loop body. M is assigned the value of n, so it's assigned 52. N is assigned the value of rem, which is 39. And now rem is assigned the value of m modulo n, or the remainder of when 52 is divided by 39, and that is 13. Okay. So now we check the condition again. Rem is still not equal to 0, and thus we execute the loop body again. So m is assigned the value of n. N is assigned the value of rem. And rem is assigned the value of the remainder when 39 is divided by 13. Well, 39 is 3 times 13, and so therefore the remainder is 0. So now rem has the value 0. Now the condition is false, as rem is equal to 0. So we skip the loop body and continue executing. So now we have to return the value n. Now, where are we going to place this so that the main function can access it? Because main does not know where the parameters or local variables or even the result of an algebraic expression may be. Well, the logical place is to place it at the very bottom of the stack for parameters and local variables of the GCD function. That way, main knows exactly where to look. So we see here that that location is here at FF, 4, and so in that location we will copy the value n. Alright, so now that return value slot stores the value 13. When we return to the main function will then take that result 13 and pass it on to the appropriate routine to print that value to the screen. Now, we're not going to focus right now on the function calls that are necessary for printing to the screen, as that requires classes and operator overloading, but rest assured that cout statement simply is converted into another function call, which then prints the value 13 to the screen. So 13 ends up being taken by main and is made an argument of an appropriate function to print that value to the screen. Now, a few observations. Looking back at those local variables, we do notice that the scope of temp and rem do not overlap. So a compiler may actually choose to allocate the same memory for each of these. Another point is that a lot more information has to be put on the stack than just parameters and local variables. For example, which instruction to continue executing at, what is the location of the bottom of this quote frame unquote for all of this information, etc., etc., etc. However, all of this will be covered in your courses on digital computers. Let's look at another example. Here we have a program that prints out the numbers of prime numbers less than or equal to an integer n. And we will do so by calling a function called n-primes. So here's the main function. We will query the user for an integer. We will then call the n-primes function with that appropriate value. Here's the n-primes function. Now, you don't have to actually understand this function to get this example, but I'm just going to step through the logic of this function. There is a parameter n, and it is of type int. First of all negative numbers are not prime, and neither is 0 nor 1. So if n is less than or equal to 1, I'm just going to return 0. Just to be sure, I'm going to assert that n is greater than or equal to 2. So this would require me to include the cassert library. Here I am declaring an array of size n plus 1, because you'll remember that arrays are indexed from 0 to n minus 1, but in this case I want to have an array of bool where I am going to access the kth entry of that array to determine whether or not n is prime. So n is the largest possible value, so I do want isPrime n to be accessible, and therefore I will set the size to be n plus 1. Therefore, isPrime is indexed from 0 all the way up to and including n. The first 3 entries will be initialized with the values false, false, and true, as 0 and 1 are not prime, but 2 is prime. And the behavior of initialization will set all other entries of that array to be false, the default value for a bool. Well, not all numbers are not prime, and so I'm going to reset all odd entries to be true for odd entries of k being greater than or equal to 3. So this will set the assumption that 3, 5, 7, 9, 11, 13, and subsequent odd numbers are all prime. What we will do then is to delete those that are not prime. How will we do this? Well, this loop looks at all odd numbers greater than or equal to 3, and starting with 3. And then, if it appears to be prime, I will then flag all odd multiples of that number as being not prime. Because if 3 is prime, then 3 times 3 is not prime, 3 times 5 is not prime, 3 times 7 is not prime, 3 times 9 is not prime, and so on and so forth. Having flagged all multiples of 3 as being not prime, we will look at 5. 5 still appears to be prime, good, and then we will flag all odd multiples of 5 as being not prime. 15, 25, 35, all of those are not prime. I do not have to flag all even multiples of a number as being prime because I've already set all even entries to be false. Once this loop finishes, then all prime numbers will still have their entry in this array flagged as true, and all composite numbers will have their entry in this array flagged as false. At this point, I just have a local variable count, which is initialized to 0, and then I go through the array, and if any entry is true, that means that that value k is prime, and I will increment the count. Having counted all the prime numbers, I will return that value. This routine can be optimized, but this is a good start. One thing I'd like you to convince yourself is that anytime we access an index in the array, we are absolutely guaranteed that the index, usually k, but in one case m times k, is between 0 and n. That means we are not going outside of the array, but you can do that on your own time. All right. Let's tabulate the information about these functions. Main has only one local variable, whereas the function n' has one parameter, type int, 5 local variables of type int, and one array of n+1 entries of type bool. Now, an int occupies 4 bytes, a bool occupies 1 byte. Okay, so if we compile this and execute it, then initially the memory for the one local variable of main is allocated at the bottom of memory, and it occupies 4 bytes. It's initialized with a default value of an int, which happens to be 0. Now, suppose the user enters a value of 10. Well, then num will simply be updated to that value. Next, we call n primes, which has one parameter n. So the memory for that parameter will be allocated on top of the stack, and it's currently uninitialized. It will be initialized with the value of the argument. In this case, the value of the argument is just the value of the local variable num. So the parameter is initialized with the value 10. Now, the function n primes has n local variables of type int. And so memory would be allocated for each of these. However, n primes also has an array of type bool. Now, a bool only occupies 1 byte, and because the array has 11 entries, at runtime an appropriate calculation will be made to determine where the start of the array should be. In this case, the start of the array to have 11 entries must be at this address here, FFFFFFD9. So if you were to print the array variable is prime to the screen, this is the address you would see. Now, of course, in reality, each compiler is going to be slightly different, and so what you see may be very different from what we're describing here. But what we want you to do is we want you to understand the idea of what is happening underneath the hood. What is happening when you call a function? So at this point, the memory for the call to is prime goes from the address ending in D9 and going all the way to the address ending in FB. If another function was to be called from within is prime, then that would use the memory above the address ending in D9. Now, when the function is prime is ready to return, the value that is to be returned will be placed in that memory location immediately above the memory allocated for main. So main knows exactly where to look to retrieve that value. In this case, the value being returned is the value of count. So the value of count is copied down to this location, and execution returns back to the main function, which will then take this return value and print it to the screen. Now, please note, this is very much so a simplified version of what's actually happening. It's much more complex than this, but this will give you an idea as to what's happening under the hood. For example, the scope of all three local variables k do not intersect. So therefore, the compiler could easily allocate the same memory location for each of these local variables. Additionally, more information is placed on top of the stack for indicating things such as where to continue executing and where the base of the call stack actually is for this particular function call, something called a frame. Also, there's so many other things to deal with as well. But what you can see now is that once the function has returned, there's a reason you can't access those local variables anymore. Because if we now call a different function after having called n primes, we're going to reuse all of this memory for that new function call. All right, so hopefully you have an idea as to what's happening under the hood when functions are called. Different computers will have different implementations, but this is a good start. Now, following this topic, you have a basic understanding of how the call stack works. The call stack starts at the bottom of memory, and as memory is required for either local variables or local arrays, memory is allocated on top of the call stack. Of course, once the function exits, that memory can be reused for subsequent function calls. This memory is used for parameters, local variables, but it is also used for storing the return value to the function that called the function in question. We've observed two examples of programs that use the call stack. Now, this is not going to be central to this course. you will be covering a lot more about the call stack and the detailed design of how programs function in your courses on digital computers. But this will help you understand how various algorithms and functions are implemented and what is actually happening under the hood. You'll see much more detail in your upper year courses covering these topics. Here's the references, the colophon, and a disclaimer. Cheers!